go. Let's see. So there are a couple questions. So Ryusei asked, will the final emphasize post-midterm 2 content? Good question. So that the final will be comprehensive, but yes, it will emphasize the stuff that is on chapters 8 through 10. And I will have a sample exam and a study guide out tomorrow. Will we get 1 or 2 pages of notes like midterm 2? The answer is yes. Same rules, 1 page, both sides. Oh yes, and a number of people have been asking, like, what can we do about revising problem sets that haven't been graded yet? Well, okay, so let's see. So let me say that. So let me say this first. So I know I keep promising, but I really will. I think I've sort of run out of room. Actually, what I've run out of is I've run out of sort of new things to be piled upon me. So I should be catching up on the homework quite a bit over the next 5 days. Before the last day class and afterwards. So I on revisions, I'll take revisions on anything up until let's see, at least until Tuesday. That's Tuesday, May 19th, the last day of finals. Okay, I shouldn't do this, but I'll say at least. And if I'm not too far behind, I'll probably take them after that if you have. So I will try to get everything graded before your final. Our final is So we're gonna have a final under the same conditions as the midterm, and our final is on Friday, May 15th. I can't remember the time. Is it 9? I think it's 9:45.
Yes, 9:45 to 12.
Yes, thank you. 9:45 to 12. And actually, it will. The final itself will, and the final itself will end, and upload will start at 11:45. So again, it'll be slightly shorter, somewhat shorter than previous finals have been. Okay, so right. So let's see. So the reading so today we're going to do 10.3. So to be clear, 10.3 is on the homework and on the final. And chapter 11, which pains me greatly, but chapter 11 was not on the homework and it's not on the final because you got to stop somewhere. And we did have like a pandemic and a quarantine and stuff. So okay, this is kind of an exceptional semester. All right, so we're at, so basically your your obligations end at chapter 10. If you tune in for chapter 11, that'd be nice. And it's really good stuff. And you might, at worst, I hope you watch it later on YouTube. Hi, YouTube, to people in the future watching this after the course is over. But yeah, I hope you watch it on YouTube at worst, because it's really cool stuff. But that's not one of your obligations. The outline for problem set 11, which is very short, is only 3 problems, is due on Thursday, and problem set 11 is due on the last day of class. And we will have a problem session on Friday, covering whatever, any questions you have left over. I'll take them. So come by, get some help. Get some help catching up. Everybody is at different places now on the homework and the exams and everything. I think everybody's sort of back in the cycle of things a little bit. And I'm really happy to see that. Thank you everybody for doing so much hard work this semester under very, very difficult circumstances. So we're almost there. And it's just 9 more days and we're good. Or 9 more days plus however much time it takes to do revisions. But are there any other questions before we get to Cosets? There's Cosets peeking through there. So we ready to go? Or ask questions?
Professor?
Yeah, go ahead.
Are you going to review before the finals?
Am I going to review? Yeah, I should, shouldn't I? Yes. John, can you send me an email to remind me to schedule a review session before finals?
Sure.
Yeah. Maybe Wednesday. How does Wednesday afternoon sound?
Good.
Okay. Let's say So possible, let me type that in the chat. Let me see if anybody responds. And people who aren't here don't get to respond, right? So there we go. Let me just sort of float. So possible final exam review due time Wednesday, May 13th, 12:30, and just 12:30 because that is the beginning of a final slot. So I mean, you sort of want these review times to line up with your final. So go check your final schedule. Let me know if that works or it doesn't. But I think that's probably my best guess as to when that will happen. But thank you for reminding me to do that. Yes, I will do that. And we don't have to get a room. That's right. So yay, that's a benefit of all this, is that we don't have to reserve rooms anymore. All right. Okay, so any other questions before we go on? Okay, and again, thank you very much for all your participation, all your hard work from all through the whole semester. Okay, so let's talk about some new stuff. And this actually turns out to be a really major idea. I mean, one unfortunate thing about not doing chapter 11 is that you won't really see why this is so interesting. I mean, you'll sort of be able to do it, and I'll ask you a question. You'll say like, these are the cosets. Okay, but it won't be clear until we get to chapter 11, until you sort of really sort of engage with that material, that it's clear like why this is a money-making idea. But okay, it's a good idea anyway. So here goes. So let let G be a group, and let H be a subgroup of G. For some random element, little a in big G, we define the left multiplicative coset. Oh my goodness, left multiplicative coset to be AH. So to be AH, which is the set A big H, which is the set of all A little h, where little h is an element of big H. So if the context is clear, so if instead of saying left multiplicative cosets, we'll just say coset. And so in this class, we're not going to talk about things that left versus right at all, like things that were AB is not equal to BA. So we won't worry too much about left cosets or right versus right cosets. And I guess let me point out that previously in chapter 7, let me blow this up a little because I think you can still see this. In chapter 7, we saw that we saw additive cosets. Cosets R plus I. Like R plus I, which is the set of all things of the form R plus A, where A is in I. So we've seen additive cosets before. Like in an additive coset, you take one fixed element R and you add everything in I to it and see all the different. And you count up all the different results you get. Here with a multiplicative coset, I can say that. So this over here was, i.e., you take the fixed element R and see and look at the results when you add all of the different elements of I to it, of the different elements of I to it. And sort of here we're doing with multiplicative cosets is that we take a fixed element A and multiply by all the different little h and big H. And you compile the results. Oh yeah, so Ryusei is asking like, where does this left come from? Yeah, so like I said, we're not gonna I know. So this is just my upbringing. I can't help but fuss about left versus right. So in a non-abelian group, AB is not equal to BA, right? So you have to worry about the order in which you in which you multiply. And so, okay, since you asked, and if you find this stuff interesting, I'm teaching Math 128A next semester. This is an excellent introduction to Math 128 because this is exactly where 128A starts. Anyway, so if you can I actually get this a draw? Yes, a right cos. If you have a right multiplicative coset, that looks something more like HA, which is the set of all things of the form little h, little a, where little h is in big H. If AH is not equal to HA, this is different. I would say dot, dot, dot. So in a non-abelian group, AH is not equal to HA, and so actually, let me see. AH is not equal to HA. You get a different result. Yeah. So in a non, because that, so there are these other things called non-abelian groups, which surprisingly enough are useful, but yeah. So there are things where the commutative property multiplication doesn't work, and there you have to worry about left versus right. For us, we don't have to worry about left versus right. So excellent question for you to say that. I couldn't help indulge myself on that one, but does that make sense? Okay. Anyway, so now we have this idea of coset, and we have seen something like that before with additive cosets. Okay, but I think, yeah, I was going to ask, like, are there any questions? But I think it's better to use an example first. So let's look at the coset. Let's look at the subgroup. Big H equals the cyclic subgroup generated by 4 in the group, the multiplicative group of the field of order 17. Or in other words, remember the field of order 17 is remember F17 is really just the integers mod 17. It's one of the most straightforward versions of a field, just Z mod P. So if I remember to figure out in a finite group, if you want to figure out the cyclic what's in the cyclic subgroup generated by 4, you start off with 4 to the 0. 1 is 4 to the 0, and then 4 to the 1. 4 squared is 16. Also known as minus 1. So 4 cubed is minus 1 times 4, which is minus 4, which is 13. 13 is minus 4 times 4 is minus 16. Oh yeah, which is equal to 1. And so and we did that last time. So that's the set of all powers of 4. All powers of 4. So everybody good with that so far? That was the cyclic subgroup generated by 4. We talked about that last time. Okay. Oh, right. And now I need some help here. So I want to. Can somebody name a number between 1 and 16? Anybody just type some 4? Okay, there. Okay. So yes, that's a very interesting one to start off with. So so what's 4H? So that's 4 times the set generated, set containing 1, 4, 16, and 13, which is, well, 4 times 1 is 4. Okay. 4 times 4 is 16. 4, oh, wait, we've done this already, right? We've done this already. 4 times 16 is 13. And so we get 13 over here. And 4 times 13, we saw is 1, right? And so 4H is equal to H. So so that's all. Yeah, thanks, Kyle. So that was actually a very important lesson. That if you take a subgroup and you take its coset sort of by multiplying by some random thing in the subgroup, then you just get the same subgroup back again. Okay, let's try 5. Oops. There we go. Oh, there we go. The arrow key. Okay, so let's try 5H. Thank you, Kyle. So that's 5 times 1, 4, 16, 13. And that gives us 5. 5 times 4 is 20 mod 17. Remember, everything's mod 17. So 5 times 4 is 20, which is 3. 5 times 6, remember 16 is minus 1. So minus 1 times 5 is minus 5 is 12. And 13, oops. Draw this more carefully. Remember, we get 13 over here. 13 is minus 4. So that's 13 times 5 is minus 20. And minus 20 is minus 3, which is 14. Okay, so that's something different. All right, good. Let's keep going. So somebody else just make up a different number. Just pick something randomly. 15, good. Okay, so let's take 15H. 15 times 1, 4, 16, 13. So that's 15. 15 is really minus 2. So minus 2 times 4 is minus 8, which is 7. Oh, no, it is 9. My bad. That was almost about to be a big mistake. This is minus 2 times minus 1 is 2. And yeah, okay. And and then now minus 2 times minus 4 is positive 8. There we go. All right. Good. Yeah. And so, wait, did I get that right? Minus 2 times minus 4 is positive 8. Okay. Yeah. All right. So, well, let's just keep going. Let me somebody give me at least one more number. Actually, can somebody give me a number of something that has not already been hit? So we got 1, 2, 3. Actually, let me go. Let's see. So can somebody name a number that hasn't been hit? So 1's been hit, 2's been hit, 3's been hit, 4's been hit. So what have we not gotten to? 6. Okay, good. 6H is 6 times 1, 4, 16, 13. Well, actually, you tell me. So you guys tell me in the chat box what's the first one? Everybody? Anybody? So what's the first number going to be? 6. Okay. All right. Next. Great. 7. So 16 is minus 1. So 6 times minus 1 is, yep. Yeah, minus 6, which is 11. And 6 times minus 4 is, yeah, okay, or 6 times 13. Let's see, that one's a lot. Yeah, 10, there we go. Okay, and lo and behold, so I want to point out here, so in these 4 cosets, so note, so these 4 cosets are all the same size. and they, so here's the bullet points are, 1, are all the same size. 2, they hit every element of G exactly once with no overlaps. And so, right, so, just by sort of playing around here, so they are all, we get all these cosets are exactly the same size, and they hit every element of G exactly once. So every element of G is contained, i.e., every element of G is in exactly one coset of H. And actually, let me sort of give you a little bit of an exercise. Well, this is something that you'll have to do for homework. This is so. Oops. I want to do this instead. Okay. So, one thing that we'll sort of see in a minute is that if you take any element of a coset, so if you take like 7H or whatever, if you take any element of a particular coset, say 7 is an element, 7 is an element of 6H, well, that means because 7, as we'll see, because 7 is an element of 6H, that means 7H is actually equal to 6H. You end up with this, you end up hitting the same. So I hope this all sounds vaguely familiar from what we did with cosets back in chapter 7. It's the same phenomenon. You can pick if you pick a different part of the same coset and use that as your sort of fixed representative in the front of your coset, you end up multiplying, and you multiply everything that fixed representative by H, you just end up getting the same coset in a different order. There's some, yeah. So this is, so I hope now this gives you some idea of what a coset is, and we made some observations that we're going to follow up on in a minute. So are there any questions about cosets so far? Cosets, man. Yeah, I don't know if you can tell, but I really like cosets. Essentially, my entire like the majority of my professional research life or whatever has to do with cosets. So I think cosets are cool, man. So, any questions? Maybe when, God willing, we eventually go back up from underground, and we get to see each other face to face again. I should actually start drinking water in class again. So it does provide a sort of convenient pause. Okay, let me go on to the next thing. All right, so I want to formalize. So what I want to do is I want to take this observation that the cosets hit everything exactly once, and I want to give a name to this. So as you have seen, if you've learned anything about abstract algebra, like what is abstract algebra? Well, it's like giving a lot of names to stuff that you kind of understood already, but somehow when you give a name to it, it really helps. I hope they can sort of see by now that one of the things that really helps in understanding what's going on with algebraic phenomena is if you name it. So here's a sort of fancy name. So describe that key property of cosets that we just talked about, that we need to make money. And yes, this is the property that this is, believe it or not, this is somehow a money-making idea. And I'll hopefully be able to explain a little bit of why that's true on Monday. We need the following idea. So let X be a set, and let A1 through AN be a collection of subsets of X. To say that A1 through AN partition X means that these sets AI are non-empty. So each of those A sub i's is not equal to the empty set. They cover X. That means that, in other words, X is the union of those A sub i's, and their pairwise is joined. They don't overlap. So yeah, I mean, so that was like whatever. this bunch of sort of abstraction, but here is the picture that really helps. So this is like A1, A2, A3. So what is a partition? It's like you take a country, the country of X, and you break it up into states A1 through A5, and the states do not overlap, and they cover every part of the country. So yeah, so that's what a partition is. So let me pull back and show you the whole page. I mean, because it is occasionally important to use the actual definition of partition, but the really important thing is that you understand this picture. So this is what it means to partition a set X into a bunch of smaller sets A1 through A5. It's this picture that you see, I think over here. I think you should see it over here. I hope I'm pointing in the correct direction. Okay, so does that picture down there? Am I pointing at the right thing? Am I pointing at the picture now? Does that picture make sense? So say yes, or ask a question in the chat if you would. Okay, so that's what it means for a bunch of subsets of capital X to partition capital X. And so the way, the sort of formal way, I think we just oops, or not. So earlier here we had this observation that the cosets hit every element of G exactly once with no overlaps. So the formal way to say that is that the cosets of H partition G. So here's a more careful way of saying what I just said. So let G be a finite group and let H be a subgroup of G. So look at all the left cosets of capital H and choose one element little a sub I from each coset of capital H, so that each of these because the thing is, you can actually, you could have 5H and 3H, and those name this, or even 4H and 1H. Here's like 1H, right? Name the same coset. So just pick one particular name for each coset, and then the theorem says that the A1 through AH, A1H through ANH partition, that set partitions G. Okay, so we want to let's see, non-empty. So we need to check. So let's go through, verify this is actually correct. So we need to check that the sets are non-empty. They cover G, and they're disjoint. Okay, and I taught my previous class starting at 9 o'clock today, and I just drew cartoons the whole time, and so I'm in a real cartoon mood today. So I'm gonna draw some more cartoons. Well, I'll start off with a non-cartoon. Oops. So yeah, let's do this. Yeah, we need to check that the sets are non-empty, they cover G, and they're disjoint. Non-empty. Well, H contains the element 1, the identity, the multiplicative identity, or you can think, which is often in our case is number 1. So A sub I times H. So A times H contains A, so it's non-empty. Okay, that wasn't so bad. So each of these sets is non-empty. They cover G. Cover. So for little g in big G, GH must be one of these cosets. And G is in GH. So G is equal to A sub I. I guess I should A sub IH, or some for one of the chosen A sub I. I guess I should be more careful and say A sub I H contains A sub I. Okay, and so here's right now I'm going to draw a cartoon. So so the interesting part of partitioning is always saying like if you have distinct cosets, distinct sets, then they have non-empty intersection. So I'm going to so for disjoint, I'm going to prove the contrapositive of that. I want to show that if AI H intersect AJH has something in it, is not empty, then it must be that AI H equals AJH. Okay, so let me draw a cartoon that explains this. So suppose, so what does it mean for these two sets to be have non-empty intersection? That means that, so here's AIH and here's AJH. I told you I was in a cartoon mood today. And they must have some element in common. Call it X. Oops. Well, actually, we don't need to make a dot for X. So this is a picture of a non-empty intersection. That is if, so suppose that's true. Then what happens? Well, we saw that that X is in AIH, which means as we will explain in a moment, and actually as we saw in practice certainly, that means that AIH equals XH. And but by exactly the same reasoning, because X is in AJH, that means that AJH equals XH, and so AIH equals AJH. Oh shoot, did I leave that out? Yes, I think I left that out. So whoops. So there's one, right, there's one lemma that one thing I forgot to prove. Okay, so let me insert that. Or at least I start. Let me explain that here. So oops. So let's go back in time, about 5 minutes, and let me state something. So so lemma, if AH, if B is in AH, then BH equals AH. Sorry, forgot about that. So proof. And actually, let me pause here and draw a little cartoon of that. So this is AH, and we have over here some element B that's in AH. So it must be the case that BH. So what we're going to show is that it must be the case that BH is actually equal to AH. So proof: if suppose B is in AH, then by definition, B is equal to A little h for some little h in big H. So because big H is a subgroup of G, any element of the form BH prime is equal to B is equal to A H prime H is in AH, since H H prime is in H. This is closure of H under multiplication. Conversely, since A is equal to B H inverse, any element of the form AH prime, which will then be equal to B H inverse H prime, is in BH. So the two sets are equal. Sorry, this is, so the two sets are equal. Yeah, okay, so this is like a slightly fussy way to do this. So see the homework problem. There's a homework problem that we sent exactly like this. Let me see if I can, where is that? Look, it's the book. This is one of the things you can do online. You can't do in like live class, huh? 140 maybe. Yeah, there we go. Right. Oh, say there. Look at all these coset things, and then remember, and there's some homework problem that you had. There's some homework problem that said like, oh yeah, if r equals s plus a for some little a, then r plus I equals s plus I. Remember that? Yeah. There we go. So this is C homework problem 7.2.3. And this is almost exactly the same thing. I think I actually just sort of gave you the answer. So go back if you're still revising 7.2.3, you can go back and revise your answer based on this. Anyway, so the point is if B is an AH, then BH equals AH, and that's what we apply here. And so, yeah, sorry, even though I had to sort of get in the time machine to get that finished, we're actually done with the proof here. All right. So anyway, well, okay. So this is not, you don't necessarily need to absorb that completely. But here, the point is that we have this the cosets of H partition G. Oh my gosh, that was probably too fast. But okay, so at least you get that. But maybe I think what you really need to understand is that what this proves is that this example here, where we sort of hit everything exactly once, and that everything sort of organizes itself into neat little piles. That always happens for any subgroup of a given group. So so are there any? I guess what I really want to ask is, are there any questions about this the statement of this theorem Are there any questions about the idea of the cosets partition G? And again, I think so yeah, I feel like maybe sort of obligated to do the proof because it's not there's some ideas going in the proof that are helpful. But but for our purposes, certainly, if you just understand the example that this is always going to happen, that you always end up hitting everything in the group exactly once by looking at the different cosets, that's really neat to understand. Okay. All right. Okay, so yeah, so there's one thing that we end up using for the fast Fourier transform, which is a thing called transversals. And again, I think really the thing to do is understand the example. So a choice of coset representatives like A1 through AN in the statement of theorem 3. Oh my goodness, I guess this was theorem 3 here. That's what I get by cutting and pasting for my code for the book. So a choice of coset representatives like we had above in the statement in that statement is called a transversal for H and G. In other words, to say that that A1 through AN is a transversal for H and G means that G is the disjoint union of exactly these cosets. And and the point of a transversal is because cosets have different names. Actually, let me zoom in again to do this. So because cosets have different names, there's some you sort of worry sometimes about like what particular names you're choose. So a transversal is a choice of a particular name for each coset. Coset of H in G. So so even as we saw back in this example over here, again, the thing to do is really to understand this example, right? This is the example is good. So as you see in this example, every coset can have different names. In fact, if a coset has 4 elements, it has 4 different names, one for each element. And so the point of the transversal is you pick a particular name for each coset. And let's see. So here, let me remind you. So H contained 1, 4, 16, 13 in G. So one transversal for let's go back and pick a transversal. All right. So here are the cosets. So I'm gonna okay. So somebody name. So again, over here, let me see. Let's see if this works. So let me put a box around these things here. There. So there's the. Oops, that wasn't what I wanted to do. So over here, there's your cosets. Yeah, that box will not stay, huh? Oh well. Anyway, so this stuff over here, those are 4 cosets. So can somebody just type in the chat, just type in one element from coset, the first coset. So can somebody type in one element, just choose one element from this coset. 1, okay, that's an excellent choice. Okay, somebody else, type in another element from this coset. Sorry, Ruchika, she beat you to it. Ruchika, you pick the next one. Pick an element from this coset here. 5, 3, 12, 14. 12, okay, good. Somebody else pick next. Somebody pick from the next. Go ahead. One of these 4. Okay, and last coset. Thank you, Nat. 8. Oh, 10, okay. So so that means so one transversal for little h in G is I guess I could just type this, huh? That's probably better. Is the set 1, 8, 10, 12. Because oops, no, I don't want to do that quite yet. Because, well, for one thing, let's try to see if we can get this to stay here. Because 1h equals, we saw is 1, 4, 16, 13. And 8h, let's see, what was that? Boy, I hope all this scrolling doesn't make people motion sick. Not bad. But here goes. 2, 8, 9, 15. 2, 8, 9, 15, 15. All right. 10h was 6, 7, 10, 11. 10h equals 6, 7, 10, 11. And then 12h equals, well, it's all the other ones. It's 3, 5, 12, 14. Okay. So there we go. So this is, so these, oops, no, it's fine. So the point is, each coset is named exactly once. named exactly once, and all the elements of G are covered. Oh, so yeah, so 1, 8, 10, 12 is a transversal because this particular choice of elements happens to give you one particular way of naming each coset exactly once, and this is like a little bit random. I mean, I guess there were there are 4 to the 4 different possible transversals for H and G. So, but you just need to have one of them for what's coming later. Okay, so well, for better or worse, that's the idea of transversal, and we'll sort of see where that. So, believe it or not, that is sort of right. So, what is the fast Fourier transform, which we're about to get to in a second? The FFT is a clever way to compute the DFT using transversals, using well-chosen transversals. Yeah, so why do I keep claiming that this is going to make you money? It's because the FFT is a good choice of transversals of a particular bunch of cosets. Madness. I know. How could that possibly be? How could this nonsense possibly make you money? But in fact, this nonsense just happens to underlie one of the most important and useful algorithms of the 20th century and certainly going to the 21st century. So anyway, okay. But like I said, and that's redundant. Yeah. Yeah. So right. I will sort of go back and look at a little bit of theory, one more bit of theory next before I sort of move on to the fast Fourier transform. But but I think this is actually the last thing where you actually have to do homework about it. So are there any questions about transversals before we move on to cover a bit of theory? So this is it. This is sort of the end of the course. Are we ready to sort of move on from this? Okay. I accept everyone else's surrender. Yeah, you got to end somewhere. That's just life. You never really finish anything. You just sort of have to stop. Maybe that came out a little bit deeper than I thought it would be. Okay, so let's. So I want to prove some theory that quickly talk about the proof of some theory that we discussed earlier. So it is a fact that if you have a subgroup H of G and an element little a of big G, then the coset A little AH has the same number of elements as capital H does. In other words, all cosets of H contain the same number of elements. So so as a corollary to that, so the one odd little fact is that let G be a finite group and let H be a subgroup of G, then the order of H, the number of elements in H, divides the order of G. And another result is that if let G be a finite group order capital N, and let A be an element of G, then the order of A divides that number. So remember, so and all right, there's always this unfortunate thing about the different meanings of order. So remember this order. Yes, it's the. Can everybody hear the police siren? It's the rigor police coming to get me, as I'm about to be maybe unrigorous. So order n means so G has capital N elements. So that's what that sense of order. That's what the word order means over here, and over here, unfortunately, means something slightly different. The order of A is remember, it's the smallest positive power of A equal to 1. And you may remember that, yeah, we saw this. In fact, we use this. We used this in our study of finite fields. Right. So, all right, and yeah, depending on which version of the midterm you took, this may have played an important part in your midterm. Right. So, excuse me. All right. So, yeah, let me prove corollary. Oh, I guess I should give these numbers. This is corollary 1. This is corollary 2. So for corollary 1, the point is that G is equal to, for some like for some choice of for some transversal of big H in G is equal to this. I'll call it K. Right. So yeah. So G is and that's the disjoint union of those sets. So there's no overlap between those sets. So if suppose H has let's call it M elements, and then each of these we just saw that each of these cosets is the same size. Each has M elements. So the order of so G must have M times K elements. Oops, and I just wrote the word melts there, huh? That's going to be confusing to people. M elements. So the reason why the order of, so cosets explain why, cosets explain why it is that that the order of a subgroup must always divide the order of a group. So because G has now M, K elements. And so the order of, which means that the order of H, M elements, divides the order of K, M times K elements. That's sort of the order of G, M times K elements. And for corollary 2, this works because the order of A is equal to the number of elements in the subgroup generated by A, and which then must divide the order of G. Ta-da! All right. So okay. So you know, so for those of you who like proofs, I think it is sort of helpful to see that it is helpful to see what, like, sort of why this is true. It's you know, it's all because, I mean, you can sort of see it here. But yeah, you know, again, if you really understand this one example, let me go back to this one example. Here, our G has 16 elements, and capital H has 4 elements. And so the reason that you have to have 4 divided 16 is because that 16 is going to be made out of disjoint pieces, each of size 4. And so, and again, because that one subgroup H is the sort of a set of distinct positive powers of 4. That's going to be the order of 4 it's going to be equal to the smallest positive power of 4 that's equal to 1, and so that also has to divide 16. Anyway, so yeah, it really all comes down to this one example. Yeah, so yeah, maybe that's a good place to end chapter 10, and before we briefly start chapter 11. So so are there any questions about this? Again, it always comes down to this example. So are there any questions about this example? Okay, at the risk of completely depleting the audience, in the last 20 minutes, I want to start something totally new that's not going to be on the final and won't be on the homework. Yeah, all right. But it's really cool. So I hope, I feel like I'm going to enjoy it. I know I'm going to enjoy it, so I hope you do too. Even if you're enjoying it somehow later after the course is over, because you're busy home working on the problem sets. Oh my God. Okay, so let me review the problem. So the problem, yeah. So the problem that we have here. So here's the discrete Fourier transform. So let omega be the natural primitive nth root of unity in C. So the point of this, actually, let me zoom in on this. Or if I had less fat fingers, that would have worked. There it is. Let me zoom on this. So the point is that fix a positive integer capital N, and let omega be the thing whose sort of natural thing, complex number whose nth power is 1. And suppose we have a signal, just some function, complex valued function, whose domain is the integers mod capital N. We define the discrete Fourier transform of little f to be f hat, which is a function from z mod n to c given by this mysterious formula here. F hat of k is equal to the average, that is the sum, over as n little n goes from 0 to n minus 1, divided by capital N. It's the average of f of n times omega to the minus nk. So that's some complex number, and so put that in. And last, we say what we saw, sort of, maybe very briefly, I indicated that if we can compute the discrete Fourier transform quickly, faster than O of n squared, then we can get fast multiplication of integers, of polynomials, and actually with more work of integers, you can actually sort of related. It's okay. It's an overstatement to say this leads to fast matrix multiplication, but it goes towards in the direction of fast matrix multiplication, and that's something that's a very active field of research right now. Like, can we sort of do some version of what we're about to see, the fast Fourier transform that will lead to fast matrix multiplication? So our goal here is a fast or faster DFT. Okay, so but in order to sort of recognize the answer, I actually want to sort of do sort of indicate like one bit of the homework, and so let's do a piece of the homework. I guess it's actually a piece of problem set 10. So I want to do just the following strange little thing. I'm just going to write out what this formula says for capital N equals 12. So let f hat of k be 1 over n times this sum. So what does that really come out to? I guess. So let's see. So I guess, yeah, I better sort of have this wider view so you can actually sort of see how this formula relates to this formula. Okay, so this right. So this is k. So here, if we set k equals 0, and this is actually, I think so. On your homework, I think I asked you to do this for like n equals 6 and n equals 8. But here's what it looks like for n equals 12. And on this first line over here was where little k equals 0. All right, so for little k equals 0, then all these omega terms become omega to the 0, and so we just get the sum 1/12 times the sum as little n goes from 0 to 11 of f of n. Okay, so that's that. And now, okay, so that's one thing. Let me do the second one, and then I'll stop and ask for questions. So if k equals 1, yeah, so, you know, this is chapter 11, but it's really testing your understanding of chapter 9. So, all right, so if k equals 1, then what we get here is f of n times omega to the minus n. And it's really taking the powers of omega to the minus 1. So this is so the terms over, so these little omega fudge factors are really going to be, actually, let me load this up so I can actually type something here. And so what we get here on this second line here, which corresponds to k equals 1, is we get the powers. Oops, I think I want this to be blue. Green is a little hard to see. This is the powers of, and now I guess I better write this in red. Omega to the minus 1. Those are the fudge factors that show up here. Over here, on the line where k equals 2, we get the powers of omega. Now, let me write the words. So here again, we get the powers. Oops. Powers of omega to the minus 2. And in general, in the, I should actually sort of write this out. If we had f hat of k in general, then the fudge factors end up being the powers of omega to the minus k. And so this is going to be like 1/12. You all start with f of 0 plus omega to the minus k f of 1 plus omega to the minus 2k f of 2, and so on. So, all right, anyway, so that's, so that is, so I just wanted to go into some detail of, and give you, look, I gave you a little help with your homework. There we go. Don't say I never gave you nothing. Yeah, so so I don't want to go into a little detail as to what this formula actually says. Right, so so yeah, and basically in line, what happens in line K is that you see, as you is that the sort of omega fudge factor terms, which is sort of that's the only thing that's different. If you look at what happens for different values of K, the only thing that changes is these omega fudge factors, and the omega fudge factors that show up are exactly the powers of omega to the negative K. That's all there is. Okay, so right, so now is a good time to pull back and ask for questions. All right, so so does this make sense for capital N equals 12? And do you think you can do this for capital N equals 6 and 8 if you haven't done it already? Is there any questions about that? So we're good? So we mod the power. Oh, you say excellent questions. Yes, we mod the powers. Excellent questions. Right. So you may notice that. Yes, fantastic question, Ryusei, which I should have remember. And all. Actually, I think I better write this up by hand. Thank you for reminding me to say that. Because omega to the capital N equals 1, all of the powers of omega are calculated mod 12. Oops, by capital N, I mean 12. So yes, Ryusei, excellent question. That's right, we mod the powers. And I think I failed to do that at some point. Yes, so omega 4 says so this should be. So this should actually be omega to the minus 4 times 11, which is minus 44, and minus 44 is minus 8 mod 12. And so this should really be minus 8. I mean, you can see all kinds of little patterns here: minus 10, 11, minus 10, minus 9, minus 8. And I think so. So the really remarkable thing about the fast Fourier, why do we keep the exponents negative? Oh yeah. So yeah, Alexis asked an excellent question. Why do you make all the exponents negative? It's a convention of this class. It's because you could actually do it the other way around. You could actually have positive exponents. Yeah, I think that deserves another page just because it won't fit in this. But I'll say just briefly. Keeping the exponents of the omegas negative is a convention of this class, of me, basically. Period. We could choose to make them positive if you really wanted to, but the formula for the DFT naturally uses negative exponents, or rather the formula. So we could choose to use positive exponents instead of negative exponents, or what's actually happened, rather the generalization of the DFT to integrals. So if you're an engineer, you might have heard something called the Fourier transform, which is you do the same thing except instead of sums you have integrals. So the generalization of the discrete Fourier transform integrals uses very naturally uses negative exponents. So note that their inverse DFT uses positive exponents, which is consistent with our using negative exponents for the DFT. Huh. Alexis, like that was like totally like an over answer to your question, but I think and essentially what I just said is because I said so, because that's the way I like it, and I'm the boss, because I'm the teacher. That's why. No, which is essentially it's essentially what I'm saying. But it is standard to use negative exponents for this. To use the standard to use the negative exponents for the forward DFT and use the positive exponents for the inverse DFT. Okay, so any other questions? You can hear my daughter sharpening her pencil in the background. Working from home is fun. All right, any other questions before let's say I want to introduce one other? Oh yeah, right. I still have to do some preliminary stuff about a bit before we get to the FFT. Okay, so just let's see, how far do we? Okay, we're almost there. So I think what we'll be able to do is I will introduce this stuff, and then next time we'll get to the algorithm itself. So I want to talk a little bit about subgroups of Cn. So remember, right, and I think the thing to do is to remind you about what's going on with C capital N, and I want to draw something. So I'm going to draw you C6. Remember, C6 is the group of sixth roots of unity. And it's exactly these complex numbers on the unit circle in the complex plane. And this is omega sub 6. This is omega squared, omega cubed, omega to the fourth, and omega to the fifth. Right, so C6 is the cyclic subgroup generated by omega sub 6, where omega sub 6 is e to the 2 pi I over 6. It's this thing over here, sixth root of unity. If you remember your trig, the coordinates of this thing are 1/2, comma, root 3 over 2. So it's 1/2 plus root 3 over 2i. Anyway, so fix a positive integer capital N and let omega be e to the 2 pi I over n. So if n is equal to d times q, so fact, if n is equal to d times q for some positive integers d and q, then CD, the group of complex d roots of unity, is precisely the cyclic subgroup generated by omega to the q. Right. Oh my God, so many d's and q's, and what the heck is going on here? Let me do it. I think the thing to do here, exactly to do here, is to understand the example. So let capital N be 12, and let omega be the 12th root of unity. So omega to the 12th equals 1. And so if we now look at the cyclic subgroup generated by omega, remember, okay, all right, we have all this nonsense up here, all this notation and like the D and the Q and the whatever. Okay, but let's look at an example. So the point is that one is the cyclic subgroup generated by omega is the powers of omega goes 1 omega squared omega cubed. Okay, even I will get a little bit tired of this. And you get to omega to the 10th, omega to the 11th, and then omega to the 12th goes back to 1. And so, oops. And so this should not be the thing generated by, but it should be the set containing. My bad. And then omega to the 12th goes back to 1 to the identity. So that's omega. And now this is, so we just said this is C12. So if you look back in chapter 9, we carefully defined that to be that's what the definition of C12, the group of complex 12th roots of unity. All right. Now, if we do the same thing for omega squared, we have 1 omega squared, omega to the 4th, omega to the 6th, omega to the 8th, omega to the 10th, and now again omega to the 12th is 1. So this finishes up. And this circles back to 1, and so what this theorem is saying is that this is C6, and remember this is the subgroup generated by e to the 2 pi I over 6. So the slightly strange thing, the slightly the confusing thing that's happening here is that in order to get the smaller, so the point of all this is that let me write this out as a sentence. The smaller subgroup is generated by a bigger power of omega. So that's the point that I'm trying to make here with this theorem, is that if you want a smaller subgroup, you're going to have to take a bigger power of omega. And so let me just go ahead and finish that up. So that's 1 omega to the 4th, omega to the 8th. And omega to the 12th is back to the beginning, and so that's C3, the cube roots of unity. That's omega to the 4th. Remember is so it's it's e to the 2 pi over I over 12, but all that times 4, so it's e to the 2 pi I over 3. And then omega to the 12th, well, omega to the 12th is 1, so if you take all the powers of 1, you just get 1, and that's C1. And we see, and you can see that each of these things is a subgroup of the next. Right, so the cyclic subgroup generated by omega to the 12th is contained in the cyclic subgroup generated by omega to the 4th, which is contained. And you just look at the sets, and you can see that each of these things below is a subset of the thing above it, and therefore is also a group and is therefore a subgroup. So we see that C1 is a subgroup of C3, is a subgroup of C6, is a subgroup of C12, and And this is, so we have this containment here. And what we'll see, so where we'll pick up on Monday for our grand finale is that this chain of subgroups, C1 is contained in C3, is contained in C6, is contained in C12. This is the algebraic structure we need for the fast Fourier transform. So yeah, comma, n equals 12. Yeah, so believe it or not, this chain of subgroups of all, and I think if you told, unless you have a highly mathematical engineer, they might have a wonderful understanding of the fast Fourier transform. But if you told them that the fast Fourier transform comes from a sort of chain of small index subgroups, they'd be like, what are you talking about? But it's true. I mean, at least from the viewpoint of algebra. So next time we'll see how to use an algebraic object like this to compute the discrete Fourier transform quickly. Okay, so let me so I'll stop recording. Bye, YouTube.